Hello. Good evening, one and all. I welcome you all to this talk. I request our Director of JNP, Dr. B.R. Guruprasad, to welcome the gathering.
Excuse me. Professor Minhyong Kim, Professor Rajesh Gopakumar of ICTS, Director, and ladies and gentlemen, it's with immense pleasure that I'm welcoming you all to the latest lecture on in the series Kaapi with Kuriosity. It's a joint program of ICTS and Jawaharlal Nehru Planetarium. Today we have a very interesting talk, the ABC mysteries, the nature of mathematics. Of course, it's both enlightening since it is philosophical also. So, nature of mathematics, the nature itself is like that. Nature of mathematics itself is like that. The added what has added more luster to this talk is the presence, the august presence of the Director of ICTS, Professor Rajesh Gopakumar. So welcome to you, sir, and thank you very much. And now I request Professor Rajesh Gopakumar to introduce the guest, please.
Thank you very much, Dr. Guruprasad, and warm welcome to all of you. It's nice to see that you've come on a Sunday afternoon to listen to the nature of mathematics. It's a particular pleasure to have Professor Minhyong Kim give this talk. Minhyong is a frequent visitor to India and in particular to ICTS, and this time also he has been at ICTS for the last week or so and given a series of talks here. So we also grabbed the opportunity to have him give a talk at this forum. I remember last time he came, he gave a very nice lecture which I missed at that time at Christ University. So this time the Planetarium, we thought we will have his talk. Professor Minhyong Kim is a very distinguished number theorist. He works on what is broadly called the algebraic number theory, but has also been pioneering an approach to number theory drawing inspiration from developments in quantum field theory and string theory, which seem to be maturing and hopefully yielding many new insights in years to come. Minhyong did his undergraduate studies in Korea and then did his PhD at Yale University under with his advisors being the very famous mathematicians Barry Mazur and Serge Lang. And after postdoctoral positions, he has been a professor at many universities, including in the UK at Warwick and Oxford, and now most recently, just a couple of years ago, moved to be the director of the ICMS, very euphonious with ICTS. So the only difference is the M stands for mathematical, whereas our T stands for theoretical. So it's an institution which has been having programs in mathematics, just like ICTS has programs in various areas of theoretical sciences. ICMS has been a venue for many interesting workshops in mathematics, but also very interestingly, something that Minhyong has been sort of advocating and actually driving a whole set of programs on mathematics for humanity, and which involves many different aspects. I urge you to look at the ICMS webpage, and you'll see some of the interesting programs under this umbrella, which, among other things, also has a component on, apart from mathematics as playing an important role in some of society's problems, but also on the history of mathematics. And there are many interesting programs on developing the history of mathematics. So, so Minhyong has, in that sense, plays a dual role, both in terms of his mathematics, again thinking very unconventionally, but also bringing in new innovative directions as the head of ICMS. So it's a particular pleasure, and I'm looking forward to hearing this very Agatha Christie sounding title. So we will I hand it over to Minhyong. So before Minhyong starts, I think on behalf of the Planetarium and ICTS, we'd like to offer a small little gift.
Okay. Thank you. Can you hear me very well? Okay. So I'm extremely grateful to the Planetarium, to the director, and to Professor Gopal Kumar for the invitation to speak here. I've been here slightly over a week, and this is my third visit to Bangalore. And each time I'm impressed by the enormous diversity of ideas, industry, and culture that you find in the city. It's clearly one of the world's centers of things to do and things to think about. It's a great privilege and an honor to be here. Rajesh has already commented on, and the director has commented on the slightly odd nature of the title, while there's reference to Agatha Christie, and I'm talking about the nature of mathematics. And this is a bit of an exception, even for me. I'm a mathematician, but I usually talk about the mathematics of nature. And so this turning around is something that I do with great reluctance, but somehow there seems to be a period in my own subject, the history of number theory, where this is sort of useful to reflect on, but I do feel a bit inadequate here because the director of the Planetarium, just before my talk, gave me a tour of the wonderful exhibits upstairs showcasing India's space program, and I was flabbergasted at the achievements that are possible through the local technology, local science, and all the efforts that people bring together. Now, I'm speaking about very humble subject by comparison, namely just the numbers, right? As I said, it's something even I speak about rather rarely, but I hope there's something in there that might be of importance or interest to you. Most of the story that I outlined, some of you will have seen the abstract, is a bit of a storm in a teacup, in the sense that there's been a great drama unfolding within mathematics, specifically in my specialty area of number theory. On the other hand, I have also commented that it's caught the public attention in various ways. The media has been very interested in this very strange story unfolding, and I do want to share with you some ingredients of the story, and I will attempt to make some comments on why the story has taken the strange turn it has. Just to give you a flavor of the attention that this story has received, I'll start with a little quote. Right? So I guess we can read it a little bit together. It spoke of the heart, an entity Grothendieck had discovered at the very center of mathematics, which had completely unhinged him. Grothendieck is a very important French mathematician from the previous century. But in any case, what this sentence refers to is not Grothendieck. It refers to this mathematician, Shinichi Mochizuki, a brilliant Japanese mathematician who's been most prominent over the last 25 years or so with incredibly deep work in my area of mathematics, number theory and arithmetic geometry. And that quotation is not from mathematics, it's from this novel called, the Spanish title was Un Verdo Terrible, which in English it was they somehow chose a different title, When We Cease to Understand the World. This was very well received when it came out in 2021. It was shortlisted for the Booker Prize. Some of you know that's one of the really great international prizes in literature, and received sort of rave reviews all over the media. And one of the figures that appear in this book is Shinichi Mochizuki from the previous slide. And this story that I'm about to remind you of or share with you was what this author tried to capture. So he goes on to speak about the events a little bit. So maybe I won't read this together except, well, okay, we will read it together maybe. On the morning of August 2012, the Japanese mathematician Shinichi Mochizuki published 4 articles on his blog. Those 600 pages contained the proof of one of the most important conjectures in number theory, known as A plus B equals C. To this day, no one has managed to comprehend it. Mochizuki had worked for years in complete isolation, developing a mathematical theory that bore no resemblance to any that had been known before. It sounds very grandiose, right? And it was in some ways. It was extreme mystery, even for a lot of mathematicians. Now, there are lots of inaccuracies in the description given here, as well as hyperbole within the quotation that I started out with as well. So when I first read this book, I didn't like it at all, quite frankly. It's very hard as a mathematician to like literature about mathematics, and about these events in particular, it's probably more knowledge than most mathematicians, so there were many things that were unsatisfactory about the way the book was written. But over the years, over the last, I guess, 3 years or so, somehow I kept returning to it. There were various aspects of the story that were hard to ignore in retrospect. And that's partly why I'm starting this story with these quotations, right? In spite of their inaccuracy and objectionable aspect of the way, well, he's exaggerating things that should not be. But anyways, so with that flavor of the public interest in this story, I will give you, firstly, this statement about the ABC conjecture. This, you don't have to read at all. I'm just giving you, flashing a slide at you to give you a flavor of the way it was originally formulated by 2 mathematicians named David Masser and Joseph Westerle. And I will also remark, whatever this means, again, you don't have to read it at all, but whatever it means, it is really a conjectural relation between addition and multiplication. That's a very odd statement to make, right? What should you say about addition and multiplication? Well, indeed. Nonetheless, it turns out to have many ramifications. For example, it generalizes a very famous theorem called Fermat's last theorem, which is about this equation x to the n plus y to the n equals z to the n, which some of you may have heard about, and it gives an explanation of the theorem in some sense. So this is a point I will return to later. But now, having shown you this mysterious slide, I'll move on to a brief timeline. So this talk, by the way, is structured into 3 parts. I should have said that at the beginning. The first is going to be somewhat sociological. Then we'll have a mathematical segment in the middle. Then conclude with essentially philosophy, where I myself won't know quite what I'm talking about. But I hope it will make some sense, at least to some of you. So here's, I'll try to give as fact-based description as I can of the events that captured the attention of a novelist, for example, right? So let's say here's what happened in 2012. Sorry?
So the conjecture was made in the late 80s or 90s?
Early 1980s. So about, from today's standpoint, I guess around 40 years ago. So it's not a very old conjecture, but the conjecture itself was rather striking, and I'll try to explain to you later why it's of interest after making some statements about it. But in any case, whatever the conjecture is, I mean, regardless of what you made of that slide, what happened was this. In 2012, about 12 years ago, there were these manuscripts called Interuniversal Teichmueller Theory I, II, III, IV, 4 long papers that was posted on the webpage of this mathematician Shinichi Mochizuki, who was a professor at the Research Institute for Mathematical Sciences at the University of Kyoto. And there was a lot of attention to it. Mathematicians, of course, paid attention, but furthermore, there was media coverage by all the major news outlets. So somehow, whatever this conjecture and claim was, it attracted a lot of attention. But curiously, Immediately after the attention, there was a lot of confusion. Why was there confusion? Because almost nobody could understand what was written there. It was so mysterious, so difficult, and filled with new notions that nobody was prepared for. 3 years later, so there was a confusion lasting certainly 3 years, right? And 3 years later, there was a workshop at the University of Oxford, attended by many leading experts in the area, including Fields medalists, Andrew Wiles, who is famous for proving Fermat theorem, and there was a lot of media coverage as well. Some of you may not know what a Fields medal is, but usually thought of as the Nobel Prize of Mathematics. So there were a number of people of that caliber attending the workshop, and the goal of the workshop was to try to figure out this paper. This very often happens in mathematics. Mathematicians find it very hard to read mathematics. It's not just you. Professional mathematicians also find it hard to read mathematics. So then they gather together to try to discuss it, ask each other, get insight from each other, and get to the bottom of the matter. So this received a lot of attention, but it ended inconclusively. People felt like they still couldn't understand, even after this gathering involving some of the leading experts in the world. So that was 3 years after this posting of the paper. Then another 3 years passed, and a very interesting event occurred. A mathematician named Peter Schulze, who's also a Fields medalist, and usually regarded as the brightest young mathematician around. He's widely acclaimed in the mathematical world. He and a colleague, Jakob Stiggs, traveled to Kyoto to discuss this proof with Mochizuki. So they traveled. So this was 6 years, remember, after the posting of the paper. But they traveled to Kyoto. They stayed there for a week, discussing and asking questions and so on. But afterwards, they released a report pointing to what they considered a fatal flaw in the reasoning. It had been pointed out by other results as well, but at this time, they went and had this careful discussion and wrote a report summarizing their conclusion, and they said, here is where the fatal flaw is. So that's what happened as a result of this meeting. And very roughly summarizing the nature of the disagreement, it went roughly like this. Schulze and Stiggs were writing, here is what you are trying to do, speaking to Mochizuki, right? And here is why it fails, right? So I'm not giving you any details, of course, but this is what they said. And then Mochizuki said, well, that's not what I'm trying to do. This, again, is not as rare an occurrence as mathematics as you'd imagine. This is very common. Mathematicians, again, typically don't follow an argument to the end. That's very common. They get the gist of an argument, make a guess about what the author is trying to do, and try to figure it out for themselves. Right? Now, I don't know how deeply they went into along the process in this conversation, but I'm just trying to say that guessing at what other people are trying to do is standard mathematics. And then they said, no, they can't possibly work for the following reason. But Mochizuki just denied that that's what he was trying to do. So somehow, there was no communication at this point after this report was released. So there wasn't much of a progress. However, 2 years later, another major event, 8 years after posting of the papers, these papers were accepted for publication. And so there was a press release announcing this acceptance, except there were the two factors worth mentioning regarding this announcement was that the publication was supposed to happen in the publication of the Research Institutes for Mathematical Sciences, but that was a journal in which Mochizuki himself is the editor-in-chief. So this is regarded as rather non-standard, and some people regard it as reason for skepticism. Right? Of course, the journal said that he had been completely kept out of the process of refereeing and accepting the paper. So it's not unheard of. So one could have viewed it in two different ways. And in any case, when they announced the acceptance of the papers, the announcement was made by two colleagues of Mochizuki, Akio Tamagawa and Masaki Kashiwara, themselves extremely senior, distinguished mathematicians in the Japanese mathematical community. So there was a lot of authority going together with this announcement as well. So this raised more confusion, in short. Then, the year after that, it was published. The papers themselves were published. 4 long papers. By the way, I don't remember if I said this at the beginning. Well, it was in the Labatut quote. At the beginning, it was over 500 pages. I think the published version eventually is over 700 pages of densely packed mathematics. Very difficult stuff. Right? So, but even after publication, many mathematicians around the world, including Schulze, who by this time has become sort of a leader of the skeptics, right? They continue to express skepticism. So then, 2 years later, amid this division of opinions, Nobuo Kawakami, who was the founder of the media and telecommunication company Dwango, he offered $1 million prize to anyone who can find a flaw in Mochizuki's proof. So that was also a very interesting development. Meanwhile, Dwango and the Nippon Foundation announced the establishment of an institution called Zen University, which works on many aspects of public education in Japan. But in fact, the university provided a home to an institution called the Interuniversal Geometry Center, which focuses a lot on the kind of topics that Mochizuki himself works on. So this was a kind of interesting twist in the story as well. And so the last of this timeline is this year in March, Kirti Joshi of the University of Arizona, he released a paper, which was the final in a series of papers that claims to fill the gaps in Mochizuki's proof. Now, the techniques that he used, of course, I won't describe it in detail, but it's something called perfectoid geometry, which is a deep mathematical theory developed, in fact, by Peter Schulze, the main skeptic. So Kirti Joshi claimed to use Schulze's technique to fill in the gaps. Mochizuki completely denied that this paper is doing anything, so he wrote an extremely angry paper denouncing this attempt. So that's where things stood. So I think what I've said here are just things that are very much in the public record, and I've tried to present it without any commentary, because it's still a very lively topic, and controversial, and it's very dangerous to comment on it in any way. But it, yes?
Who is going to, who did this company mention a mechanism by which the proof would be, the flaw would be judged, and the person who found the flaw would have a process of judging whether
how to give the prize, you mean?
Yes.
Yes, they have something. I haven't read that carefully enough to comment on it, so I won't comment on it.
So, but Peter Scholz and Stix's comment do not count?
Well, first they have to submit it in some way, but I don't think they did. That much I know. I think they do have to submit it as an official entry in some way. I don't think they did.
And so Kirti Joshi seems to therefore believe that the proof that it can be corrected.
That it can be corrected. He thinks it's basically correct. So Kirti Joshi, in his papers, he presents it as essentially Mochizuki's proof, except expressed in different language. That's the way he expresses.
And Mochizuki is unhappy because he feels that this was already done.
Exactly, yeah, that's the essential. Of course, you'd have to ask him to get a precise, but that's my impression of the situation. Okay, so that's the timeline. I hope it makes some sense and gives some sense of the confusion in the mathematical community that's gone on now for 12 years. So to summarize very briefly the current status after the timeline, I think it's fair to say this itself can be viewed as a controversial statement. Well, I'll go on the limb and make it. Most mathematicians who have an opinion appear to accept Schulze's judgment that there's a fatal flaw in the paper. That does seem to be the majority feeling among many mathematicians. And Schulze also believes that Joshi's paper is flawed, but he does think that some of the ideas contained in them have promise. So that's a kind of an interesting reflection on the effort that Joshi made. Now, there is also a small group of mathematicians who believe Mochizuki's paper to be correct, And they've continued to develop the theory and find new consequences, find stronger results. That's what typically happens with mathematics. Somebody announces some results, and other people generalize it, strengthen it, look for consequences, and so on. So some people have gone on to do this. So this statement is a small group might itself be controversial, but I think I can defend that in some way. But it also needs to be pointed out, this next statement, that among the people who doubt the results of the paper, the number of people who have seriously tried to understand the paper, I think is probably less than 10. This is sort of a random number I'm pulling out, but it's certainly a very small number of people who have themselves tried to read the paper and understand it. So the skepticism might be something that you're also skeptical about from that point of view, right? But so this last situation, this last statement, of course, raises lots of almost fundamental questions about the nature of science, right? Because in some sense, to do science, we all rely on other people's opinions. We sort of rely on the opinion of people whom we trust to tell us whether something else is trustworthy. This is a very common way to proceed even in science. On the other hand, we also believe that we should only have opinion about things that we ourselves fully understand. That's also a principle that we feel we should follow. Of course, any normal person tries to find some balance between these two approaches, sort of relying on the community opinion and trying to understand oneself. You have to find some balance between this, but there's no formula for where the correct balance is, right? Everybody has to somehow figure out for themselves in the different situations. So this is part of the reason why it's such a confusing situation. Is it reasonable that so many people are doubting even though they haven't read the paper themselves? You might think that's unreasonable. Some other people might say, well, this is normal in science. That's how we proceed anyway. You can't try to understand everything yourself. So this, in some sense, is the crux of the sociological problem that this paper has raised. Okay, so that's a timeline and a summary. So, sorry, I guess I forgot to mention that. I mean, I suppose it's kind of obvious, but the reason that so few people have read this is that even the completely well-established mathematics, that's the starting point of the paper, is regarded as extremely difficult. It's among the most difficult areas of mathematics. But then on top of that, Mochizuki has laid an entirely new layer of terminology, ideas, and his own theories. So it makes it completely a formidable task to try to read this paper. That's why so few people have engaged with it. Right. So with that sociological part over with, now I'll move on to the mathematics. Any other questions at this point? No.
Category you belong to.
Sorry?
I'm very curious to know in which category you belong to.
Do I belong to? I find I sympathize with basically everybody. It's an honest statement.
So amongst the people who attended that conference in Oxford, probably there were more than 10 people, but you think that not all of them had equally seriously engaged with the
most of them did not. They paid attention to the talks and they asked some questions and so on, but most people did not seriously try to read the paper and understand. There was a question over there.
So you said that the starting of this paper deals with very difficult areas of mathematics, and what areas of mathematics are they?
What areas are they? Very good question. So yes, it belongs to something called arithmetic geometry, where people try to combine in the study of numbers and study of shapes into one piece. But this combination makes things very, very abstract somehow, because you have to view numbers and shapes as somehow being the same thing, right? That means that you have to take a very long distance view of both kinds of objects to combine them. So that already starts up the difficulty. Thank you very much. That's a very good question. Any other questions so far? Again, I didn't present this in a very systematic way, but I hope you can have a sense of the confusion that still exists within our community. Okay, so now I'll move on to the mathematics. And it really, as I said at the beginning, it really is about addition and multiplication, right? But of course, any normal person will ask, so what could there possibly be new to say about addition and multiplication? Right? However, you could take the converse view, and this is the view I would take. If there is something new to say about addition and multiplication, it must be really very groundbreaking. After all, this is completely elementary thing that everybody learns in school. If there are new discoveries made about this somehow, this can't be a normal thing. So this must be somehow something very fundamental. And that's part of the reason that these conjectures are regarded as so important, because they are supposedly, if proved, they are a new discovery about the relation between addition and multiplication. So more precisely, the ABC conjecture, so I'm going to describe to you what this conjecture says in relatively concrete terms. It proposes an answer to the question, what do the prime factorizations of A and B separately tell us about the prime factorization after you add the numbers together? So this is precisely the question that the conjecture tries to answer. I'll remind you what this question is about, right, by way of some examples. So what is prime factorization, first of all? I'll remind you, this is the kind of thing you do to factorize a number. If you take 10, you can write it as 5 times 2. 12, you can write as 2 times 2 times 3. You often write it as 2 squared times 3, right? When I write 13 equals 13, that means 13 itself is a prime, right? It doesn't break up any further, and so on. So is everybody sort of comfortable with the idea of prime factorization? Are you okay with it? Okay, great. Yeah, no, I'm going to keep asking you a question to see how I'm doing in this lecture. Okay. So there's this way of trying to break up a number into a product of other numbers, yeah, until it can't be broken up any further. Those are what the primes are, right? And any number can be written as a product of prime. That's its prime. That's the number's prime factorization. And these are some examples. Now, a little bit of terminology. I won't write too many abstract equations like this, but a few here and there in order to explain the words I'm using. If you write a number as a product of primes in this way, right? So again, some prime occur many times, like over here, right? So the number of primes, times that a given prime occurs inside this factorization is called its multiplicity. It occurs multiple times, that's what we're saying. So it refers to, so we call it its multiplicity. So for example, so for this number has this prime factorization that looks like this. So 2 has multiplicity 2, right? And 17 has multiplicity, do you know?
Yeah, that's going to have 3.
Good, very good. Okay, so I'm on the right track. So 17 has multiplicity 3, and all these other primes have multiplicity 1 inside this factorization, right? So that's what I mean by this multiplicity. So it is a simple notion, but something that we really have to focus on to understand the ABC conjecture. Right. But as before now getting to the conjecture proper, I will insert even here a slightly philosophical remark, right? Why should somebody be interested in these primes? Yeah? Sorry? Ciphers. Ciphers, okay, that's a very good answer. So, but that somehow belongs to the realm of mathematics of nature. So I'm going to try to give you an answer that's closer to nature of mathematics. Well, some combination of the two perspectives, right? Thank you very much. So primes are very much used in coming up with very secure cryptography, ways of encoding messages so that you can use it on the internet. That's a very important application. But people were, by the way, interested in primes long before cryptography as well. Yeah, long before that method. So you could again ask at that point, why are these crazy number theorists interested in prime? I sometimes feel like that, by the way. Even though I'm a number theorist, I feel like, what are these? How can you possibly be interested in such elementary things? So I'll give you one answer. So you'll often see an answer of this sort, that sort of the way it was part of the discussion of prime factorization, you can view primes as being the elementary building blocks of the natural numbers, right? Any natural number can be written as a product of primes. That's exactly what we said. So they are elementary building blocks. But when somebody tells you something like this, part of you should be skeptical. I used to be quite skeptical, right? Why? Because 1 is the elementary building block of numbers. After all, any number can be just written as 1 added to itself many times. Why do I insist on primes? So if I'm going to insist on primes as being elementary building blocks, that means that in some way, multiplicative building blocks I'm claiming is somehow more important, right? This multiplication is somehow more fundamental as way of building up numbers. And that is true. So that's where I'm going to give you a slight philosophical remark. And the key point is that it's multiplication, not addition, that is the basic model for combining two objects to get a composite object. So this is a statement that I won't justify in full detail right now, but it is true. That is to say, when you multiply two prime numbers to get a composite number, that is very similar to a process like combining two atoms to get a molecule. So this way of getting composite objects out of elementary objects is very much modeled by multiplying primes to get a composite number. Did you have a question? Uh-huh.
So the question is that the justification that you give that the key point is multiplication and not addition. A prime number is basically you have, meaning its factors should be anything else than 1 and
it can't
the
be
same
broken
number.
down. That's right,
So if it's 1, it does not have any other factors than 1. And so 1 is the only factor because it is
That's
both
right.
1, the fundamental number, and also the same number. So why not a prime number?
Why is 1 not a prime number? So you could count 1 as a prime number if you'd like, right? But part of one reason is, so I don't know if you like this reason. It's not so easy to answer that question in a satisfactory way. It's a very good question in some way. And so mathematicians like me will often sort of wave their hands and get a bit confused when you ask that question. I'll try not to get confused. But part of the reason is exactly this. If you look at this, right? If I try to write a number as a product of prime numbers, I don't really need to write 1 explicitly anywhere, right? So it's not, there's some strange sense that when we think about multiplication, 1 isn't necessary as a building block. Does that make sense? Except for 1 itself. Anything else, we don't really need 1. So that's one reason not to regard it as a building block. But it's also related to this objection I had. If you were thinking of building numbers up out of addition, you wouldn't need 0, right? You don't need 0 for that, right? So in some sense, in this building block point of view, 1 is kind of superfluous. That's one way of it. Does that sort of make sense? Okay, thank you for that question. Okay, but now I'll return to this point that in fact, multiplication is one of the very basic models for combining two objects to get a composite object. So I'm just going to try to give you a slight feeling for this, but there's also a kind of philosophical terminology like about of this art regarding this. When you multiply numbers, this is the most elementary part of a process that people sometimes call synthesis. There's an old philosophical terminology. Combining objects to get a new object is called synthesis. Taking objects apart to see what it's made out of is sometimes called analysis. From in old philosophical terminology. So from our point of view, multiplication of numbers is the most elementary kind of synthesis, while factorization is the most elementary kind of analysis. Yeah, it occurs very much in chemistry, of course. And now, the reason that combining objects is similar to multiplication, so here I put 2 sentences, which maybe won't make much sense to you right now. I'm putting these sentences here sort of as statements for further reflection rather than something I'm going to explain at a great length right now. But when you talk about any object, right, it can come in a number of different states. It's not in a single state. It's like even right now, I'm moving around all the time in front of you. My temperature is changing, right? I ruffle my hair like this, right? I can do all kinds of things. You still think it's me, right? So there's a whole collection of states that defines who I am. Yeah? And when you combine 2 different objects to get a new object, in fact, the state of the new object is specified by a state of A and a state of B. You need to know both. So that's sort of the process of multiplication. So to take a very elementary example to give you a sense of what I mean by that, if you throw a die, how many possible outcomes are there? There are 6 outcomes, right? But if you throw 2 dice, there are 6 times 6, 36 possible outcomes, right? So this is exactly this process, whereby multiplication is reflecting the composition of objects, right? And this permeates all of physics as well. It really, the process of building up a molecule out of atoms really is multiplication. I hope Rajesh agrees. Anyways, so this is my way of justifying why multiplication is what we're focusing on when we talk about the building blocks even of numbers. Okay, so that's, again, probably a passage that, as I said, I put on the slide more for further reflections rather than claiming that it's a real explanation of some sort. Okay, but now let's move on to the ABC conjecture itself. I'm going to start with a very rough view of what the conjecture says. So the essential question, as I alluded to earlier, is when you add numbers, how does this affect prime factorization? That's exactly the question that we're going to try to figure out. So here are some examples. So 25 is 5 times 5. 9 is 3 times 3. When you add the 2, you get 34, which is 2 times 17, right? So that's the factorization. Let's keep going a little bit further. 45 is 3 squared times 5. 77 is 7 times 11. Okay? So that's the prime factorization here. When you add the two numbers together, you get 122, which is 2 times 61. So how do the prime factorization of the sum somehow reflect the prime factorizations you started out with? The obvious answer is, and it seems to be completely unrelated, right? You can't, the prime factorization of the sum that you get seems to be completely unrelated to the prime factorizations you started out with for the two numbers separately. Does that make sense? So somehow, this, well, it's hard to, another way of saying it, it's hard to predict anything about the prime factorization of the sum, A plus B, just by knowing about the prime factorization of A and B. You just have to do it. There's no other way. I want you to compare it briefly with this very silly slide. So what am I doing here? I'm taking the same numbers, 25 and 9, and multiplying them. And same for each of the other pairs I gave as examples in the previous slide. When you multiply them, the prime factorization of this product is completely evident from these, right? You just put the prime factorizations together. That gives you the prime factorization of the product. There's nothing mysterious going on there, right? Again, because prime factorization was this process of breaking things up multiplicatively, right? So when you combine numbers via multiplication, it has a very transparent factorization that you can just read off from what you had before. You don't have to factorize again, right? But in the addition slide, these factorizations are somehow random when you compare with what you started out with, right? So there's a certain clash between addition and multiplication when you start thinking, asking yourself this question. So here are just a slide of many examples. So you don't have to read this very carefully, but I'm just trying to illustrate this with factorization of some large numbers. So here are A and B. So here, for example, is the factorization of 123,405. This is the factorization of 345,600A. When you add them together, so here's the factorization you get. Again, there's nothing about these factorizations that would have enabled you to guess anything about this column over here, right? That's what the way each of the rows are made up. Does that make sense? Yeah. So this column looks quite random when you compare it to these two. Yeah. So that's the basic idea. So, as I said, the essential question is there any definite relationship at all between the prime factorizations of A, B, and A plus B? It doesn't look like it from the previous slide, right? Doesn't seem to be any particular relation. But the ABC conjecture, in fact, says that there is one. There is a subtle or relatively precise relation. And this is the quite surprising relation between addition and multiplication that the conjecture is proposing. Okay? So now I'll try to explain what the conjecture is saying. First loosely, then precisely. So as I already said this earlier, but I'm repeating, to get at the statement of the conjecture, you need to consider carefully two things. the size of the prime factors of a number, and the multiplicity, which I called your attention to earlier. Okay? So, by the way, so this is a slightly simplifying terminology I'll use in the subsequent slide. If you have three numbers, A, B, and C, this is about the ABC conjecture, so I'm always calling the numbers A, B, and C, right? With C being A plus B, these are not three independent numbers, but C is always A plus B from in the subsequent discussion. I'll call such three numbers on ABC triple from now on, okay? Yeah, so again, 2, 3, and 5 is an ABC triple, but 3, 3, and 7 is not, okay? I'll be referring to ABC triples for simplicity in the subsequent slides. So I'll first give, I forgot, I wrote 3 informal descriptions. There might be only 2. Let's look, I forgot. I may have changed the slide in the meanwhile. So what does the ABC conjecture say? Given an ABC triple A, B, and C, so the ABC conjecture is about the prime factors of A times B times C. Now you take the product of the three numbers, right? So in other words, A, B, and A plus B. You take the product of the three numbers, and the ABC conjecture says something about the prime factors of that product. What does it say? Well, one very loose description is that not too many primes of high multiplicity can occur in A times B times C. So that's a very loose statement. Some primes can occur with very high multiplicity, but not too many. I'll give you another more precise statement. Okay, there were 3 informal descriptions. If some prime occurs in A times B times C with high multiplicity, then this has to be balanced out by some larger prime occurring with low multiplicity. This sentence is slightly hard to understand, right? So I'll show you examples in the next slide to illustrate this. But the third statement is that in some sense, the average multiplicity of primes in A times B times C cannot be very large. And I'll say in a few slides exactly what the not very large means. Okay? So at first, let's look at examples. These sentences won't make much sense to you right now, but the examples should make it clear. Okay? But I'll first note that, remember, because of this, what happens to prime factorizations when you multiply numbers, to talk about the primes that occur in A times B times C, this is the same as the primes that occur in one of these three numbers, A or B or C, right? Because they'll occur somewhere exactly like they occur in the product. Okay, so here's a picture, a table rather. So here, I'm going to take A to be powers of 2. So in fact, I've taken relatively large powers of 2, right? Okay? And I'm going to just take B to be 1. That's very, very simple, right? So when I add B to A, so here are the numbers I get. Now I factorize the number here. Okay? So I've arranged it so that 2 occurs with very high multiplicity in A, right? And B is just 1, so there's no prime factors there, right? But now, if you factorize A times B, you get not much multiplicity, right? Everything occurring there has rather low multiplicity. So this was the phenomenon I referred to earlier. So I'm going to give you an even more larger example. Let's take A to be 2 to the 50th power. That's a very large number. Yeah? Even by standards of cryptography, this gets to be a fairly large number at this point. Right? And take B to be 1, then A plus B is this. When you factorize A plus B, here's what you get. Again, all very low multiplicity, right? So this is the phenomenon I referred to earlier. If you make some primes occur with high multiplicity, then there will be some larger primes occurring with low multiplicity. This is typically the case. I'll show you another slide with more examples. This time, I'll take both A and B to have prime factors of high multiplicity, right? That's what I've done. I've added them together here in the third column and factorized. And again, you get low multiplicity everywhere, right? Does this make sense? Any questions here about this slide?
I mean, if you put a number here and then front and back, you see that there are prime numbers that exist that can multiply to form this number. Because there are a sufficient number of primes for that property. So doesn't that make it a bit self-evident that the multiplicity is going to be low because those primes already exist? We know that.
But you could have primes occurring here. So what would have prevented primes occurring here with high multiplicity again? What did you say prevents primes occurring here with high multiplicity?
I mean, if you have any number,
right.
no matter how large it is, then on either side of the number in the number line, you have sufficient number of prime numbers to comprise that. Like,
sure.
So,
well, but these numbers have very high multiplicity, right?
Yeah, but that's not what you're looking for, right? You're adding them. You have a number with high multiplicity, but that is irrelevant to the sum itself.
That's right. So actually, you probably have a pretty good intuition for numbers, right? In making that observation, and it's possible that you can view this as very natural in some way. Okay. So if that's the case, that's fine, and I'll try to make a more quantitative statement about that later. Okay. Other questions so far? No? Okay. I'll show you one other example. Again, this time, I'll take both A and B to have very, very high multiplicity. 2 to the 50th power, 3 to the 50th power. Okay? If you add them, you get this large number over here. And when you factorize that, here's what you get. No multiplicities at all when you do that. So this is the typical phenomenon, which hopefully, if it's already sort of evident to you, I think that's good. But again, we'll try to make quantitative statements about that in a second. Other questions? Sorry? No? Okay. So now I'm going to explain. So what I've done so far, by the way, is I've sort of explained the first two statements. That there aren't that many primes of high multiplicity that occur in A times B times C. And also, if there's some prime occurring with high multiplicity, that's somehow balanced out by large primes occurring with low multiplicity. That was illustrated by these examples, right? But now I'll explain the third business about averages. And the average I'm talking about is something that we'll call a weighted average. Right? So what is a weighted average? Well, if you take two numbers, m and n, their average is just this, right? You add them and divide by 2. If you have three numbers, you add them all up and divide by 3 and so on. Everybody knows averages, I think, right? Well, what is a weighted average? It's something like this. You can take two m and n, but add twice of n to m, and then divide the result by 3. Or a weighted average might look like this. 3m times plus 2n and divide by 5 and so on. Or there might be weighted averages like this. So this is a very common notion in mathematics as well. Sorry, this is again a slight abstract notation. But if you have a collection of k numbers, w1 through wk, then you can form a weighted average of any other collection of k numbers. By adding each number up with these weights multiplied to the front, and dividing the total by the total weight, dividing by the total weight of everything. That is called a weighted average. Why might one consider something like this? I'll just show you one example. Right? So in a lot of these different situations where you're computing averages of numbers, where the numbers vary in importance. Some numbers might be more important than others when you're averaging out. For example, each of these AIs here might be the share price of some company, right? But the companies might be of all different sizes, so the outstanding shares of any given company will vary greatly depending on the size of the company. So if you form a weighted average like this, where the weight is the number of shares of that company, right? This is a much more faithful reflection of the state of the market than just taking the plain average, right? Because again, if you have a company with very large number of shares, that's a large weight here, a little difference in their share price will affect the market much more seriously, right, than the smaller company. So this is one example where weighted averages will occur, but it's much more general than that. So now I referred to the fact that the ABC conjecture says something about the kind of average multiplicity of ABC triples. Yeah? But in fact, what it is exactly, it's a weighted average multiplicity. What do I mean? So if you take a number with a prime factorization that looks like this, the weighted average multiplicity is this complicated looking expression. But what are we doing here? What we're doing is we're averaging all these multiplicities that occur inside the primes, right? Except we're weighting each multiplicity by the log of the prime that it belongs to. Now, this log is a number that you may know or not. It's okay if you don't know it. You should just replace log by the length of the number. It's the same, essentially the same quantity as the length of the number. So each prime should be, the multiplicity of each prime is just weighted roughly by its length. The amount of information contained in that number, that's another way of thinking about it. So for example, if you take a number like this, right, with prime factorization looks like this, then the normal average multiplicity will be 4 plus 2 plus 1 divided by 3, right? So it's 7/3, but the weighted average multiplicity turns into this quantity. 7/3 is somewhat more than 2, right? But here it's 1.37, the weighted average multiplicity. So here's another example. Well, actually, maybe I'll directly skip to the next slide. So this was one of these examples that we had earlier, right? 2 to the 50, 3 to the 50, then A plus B was this thing, right? Now, if you just take the average multiplicity of A times B times A times B, A plus B, then what do you have? You have 50 plus 50, but then multiplicity 1 for each of these 5 primes, right? So here's the normal multiplicity, and you get exactly 15. Right? But if you take the weighted average multiplicity, here's what you get. It's about 2.55. It's much smaller than the average multiplicity. Why? Because these large primes have low multiplicity, and they are contributing much more to this weighted average than the small primes. So that's what's happening over here. Okay? Right. Now I'll give you the actual statement of the ABC conjecture. So this is essentially a precise statement. One can refine it in various ways. But here's the statement. So if you take ABC triples A, B, and C, then the weighted average multiplicity of primes in A times B times C is almost less than 3.1. That's a very strange statement, right? But we saw that actually in this example, it was 2.55. The previous example, actually, I didn't show it to you, but it was 2.316, right? And in fact, it's almost always less than 3.1. What does this almost always mean? Well, actually, it means that there are only finitely many exceptions. There are only finitely many AB strip triples that violate that inequality, right? Or it's bigger than 3.1. That's what the conjecture is saying. In fact, some people computed this for a whole ton of ABC triples, right? More than a quadrillion of them. And that inequality is violated for less than whatever, your percent of them. It's very, very few ABC triples where that inequality is violated. And the largest weighted average multiplicity that you'll find, even among the known that there is an upper bound, like this, unless you believe Mochizuki's proof. That is. So by the conjecture by itself, it doesn't give you. We don't know. So in fact, that's what I was about to say right now. If the ABC conjecture is true, then clearly there is an upper bound. There's some number for which the ABC weighted average multiplicity for any ABC triple will be less than K. Why? Because they're less than 3.1 for all but finitely many, right? Then if you just take the largest weighted average multiplicity or the remaining and take that to be K, then that's an upper bound for all possible weighted average multiplicity. Because remember, I said that ABC conjecture somehow generalizes Fermat's last theorem, right? So I'll explain that briefly right now. Now, Fermat's last theorem will tell you that this equation, if this equation is satisfied by non-zero natural numbers, right, then the only way they can be satisfied is if n equals 1 or 2. If n is 3 and above, you'll never find non-zero natural numbers that satisfy this equation. That's what Fermat's last theorem says. It was approved by Andrew Wild. Now, it should be noted when n equals 2, there are plenty of solutions. But as soon as n is 3 or above, there's never a solution. Okay? And the reason, one way of thinking about that in relating it to the ABC triple is this. If you have A is x to the n and b is y to the n and c equals z to the n as occurring in Fermat's last theorem, you can take these to be an ABC triple, right? So then, A times B times C, if you compare it to the prime factorization of X times Y times Z, if that looks like this, then A times B times C, all the multiplicities just increase by N, right? A factor of N. So if you take the weighted average multiplicity of A, B, and C, it will look like this, but that's just N times the weighted average multiplicity of X times Y times Z, right? So whatever this is, the weighted average multiplicity of this triple will be bigger than N, right? But then N has to be less than K. So this proves Fermat's last theorem for all but finitely many possible exponents, right? But it's even more than that to my mind to some extent. Of course, there are these finitely many small exponents that you have to take care of, but the most interesting part is that all possible large exponents have no possible solutions. And so equations like that, it may have appeared a bit random to you when you first heard about Fermat's last theorem, right? But in fact, from the ABC conjecture point of view, it just explains the phenomenon in terms of general properties of addition and multiplication of numbers. So that's the sense in which it explains the theorem. Okay, so I'm told to quit in 5 minutes, but actually I did start at 5:15, right? Right. So I'm almost done anyways, because the rest is about just philosophical comments. Question?
You said there was a equation you gave x power n ABC conjecture. The previous slide.
Right. This one?
Right.
Or
yeah.
here?
You said n should be equal to 1 or 2.
That if n is bigger than 3,
it doesn't
there's
holds
never,
good.
you never get this equation.
Is it related to weighted average, that number which you gave, it should be less than 3.1?
Is it related to the 3.1?
Yeah.
Not quite, not quite. No, there's not no obvious. That's a very good question, but there's not an obvious relation that with that previous 3.1. Now, thank you for that question.
I have one more question.
Sure.
You started like saying that when we have two numbers with with high multiplicity, when we add and find the prime factorization of it, that will have a very low multiplicity, right?
Right.
But the converse, I was thinking, when we have two numbers with very low multiplicity, even though we add that number and find the prime factorization of it, there are cases there where we'll end up getting the low multiplicity.
Right.
Why that statement was taken in the first place is what my question is.
When all three have low multiplicity, you're saying, right?
Yeah, exactly.
So those cases are, those would be those situations where the weighted average multiplicity is quite low. Certainly less than 3.1 if they are all very low. But what I was trying to show with my example is that even if you artificially try to make two of the numbers have very high multiplicity, the third one will necessarily have low ones. So that was the point of the example. Okay. Does that make sense? Yes. Those cases are sort of okay almost without further thought. Okay.
Thank you, sir.
So to excuse myself to the host, there have been a lot of questions in the course of the talk as well. So I hope it's not too objectionable that I'm going somewhat over time. So I won't say much about this actually, about this portion. So the point is that, so here's the portion of Mochizuki's paper where Chote and Sticks claim that there's a proof, there's a flaw. This is the precise portion. And it's slightly hard to see, I see now, the typesetting is not quite right. But in any case, it probably won't make any sense to you, but that's okay. It doesn't make sense to most mathematicians, right? So it's quite difficult mathematics. So I've also shown you copied a page from a fairly well-referenced book on algebraic geometry by this person, Alexander Grothendieck, right, who was referred to in the first slide. Right? So it's just a lot of text. But the point I want to make, why am I showing you this, is because you'll see some technical-looking equation and you'll see a lot of words. And most mathematics is like this. There's another view of mathematics that became popularized sometime early in the 20th century, and it looked like this. This is a view of mathematics that some people had. And somehow it still influences people's ideas about mathematics. And sometimes it's very harmful for pedagogy. Because some people have the idea that mathematics should be about mechanical reasoning. And it's never like that. It's some combination of ordinary language combined with some things that look a bit more technical. So when these philosophers, Russell and Whitehead, were writing papers like this, what they wanted to do was they wanted to make all of mathematics look like that. There was a very famous program about which they wrote very long books themselves, which eventually became very important in computer science. Right? And they wanted to do that. Why were they so interested in making mathematics like that? Because they wanted mathematics to give you absolute certainty. They thought mathematics should yield absolute certainty. So they thought for it to yield absolute certainty, it should be somehow very mechanical and machine-like in nature, right? Now, absolute certainty, or not absolute certainty, but lack of errors is very, very important in computer science. Why? Because our program doesn't run if there are errors. Right? But human mathematics, which is done by humans, is not so sensitive to errors because it's about human understanding, which proceeds in stages through approximations. And that's okay in the advancement of our understanding. We don't have to get every factor right exactly at the beginning, right? And so there's been a lot of pedagogical and philosophical confusion about this nature of mathematics and mathematical proof. And that has somehow also informed the confusion about Mochizuki's proof as well. Because, of course, for a paper like that, you're not going to, so I'm going to actually skip to the conclusion, more or less. You see, the ABC story is viewed by many mathematicians as something of a failure. There are people who say it's such a big embarrassment for number theory and for mathematics. Why? That a proof has been left standing for 12 years. How could something like this happen? Mathematics should strive for clarity and certainty. Now, I don't think this is a problem at all, in my view. At some point, I hope it will be resolved. But in fact, this idea of mathematics as something that gives infallibility is what you might call a perfect, flawless crystal model of mathematics. They think mathematics is like a crystal, which is perfect and beautiful, but which a single flaw will cause to shatter. Some people are worried about this idea. And they're partly worried because they have this model somewhere in mind. But mathematics itself is more like a biological neural network. It in fact does normally have many flaws, but it does have a robust process of growth, sometimes decays, but it also has a complex mechanism of self-correction. And it relies on a lot of nourishment from the outside. And so the confusion surrounding a story like the ABC conjecture, my impression is that eventually it will contribute to enrichment of mathematics in spite of the current day confusion. Yeah? Because that's the way mathematics normally works. We will never have absolute certainty about anything when we try to understand the structures and patterns of the universe. Right? But that's normal. That's the way any science proceeds. And that's the way we try to improve our understanding gradually. And I'm almost certain that regardless of how the ABC story turns out, it will in the end have improved our understanding. Okay, before I get mobbed by the host, I think I should stop there. Thank you very much for your patience. Sure, sure.
Does the ABC conjecture have anything to do with the sparsity of primes as they grow larger? I mean, just short in the, I don't know about it, but is it possible?
It certainly has something to do with it. There are some definite connections that are sort of hard to state right now. It's a bit technical. So I think the short answer is yes, right? But to explain that yes is not so easy at the moment, sure. Right? But because I was in a little bit of a rush at the end, sorry. But I should have also emphasized this point that I hope you find this very strange, the statement itself. Right? This idea that somehow you almost never get something bigger than 3.1. Isn't this a very strange thing? That when you take this weighted average multiplicity of A, B, and C, how could it be that this is always typically so low? It's a very strange thing. And this is exactly the new fact about addition and multiplication that the conjecture is proposing. And so therefore, if it's true, it tends to have many, many consequences. Thank you for your question.
A related question, if I may. If we think of primes as kind of coordinate system in which other numbers live,
Right.
does this imply in a very physical way that the universe of numbers is somehow bounded in a very physical sense?
Very interesting. I would say what it says is that it's not all numbers, by the way. Here I'm only considering weighted average multiplicity of ABC triples, right? But what it does seem to say is that the information content there is somehow bounded. That does seem to be what it says. And there are some physicists in the audience, so I might point out, if you look at this definition of weighted average multiplicity, there's this kind of artificial physical system called primons. Do you know about them? Are you sure? It's some very strange physical system that are labeled by primes. And this here is a ratio between the entropy of some bosonic states and some fermionic states. So so this leads one to ask whether there's some physical interpretation of the inequality itself. I don't know of any. Anyways.
Hello. Sir, given its sociological importance, like, has there been any attempt to write a popular book around ABC conjecture? Just like how science...
There is. I haven't read it, but there's a book by Fumiharu Kato, who's a close colleague of Shinichi Mochizuki. It was published in Japanese. And the NHK, the Japanese national TV, made a TV program about this as well. So there have been a number of attempts to popularize. I myself have always been somewhat afraid of talking about this, even in a lecture like this. Because, to be honest, having given this lecture, because this is being live streamed, I'm quite worried that I'll receive a lot of criticism from all quarters. I almost feel virtually certain that I will, so I have to learn how to grow a thick skin. But anyways, at this point, the reason I'm talking about it is, and I think this is what your question is suggesting. I think this story is very interesting anyways. So I feel, because I also spend a lot of time, especially in Korea, doing public communication of science and mathematics, I feel a certain duty to tell this story, even if I get criticized for it.
So has there been any historical analog to like a problem where there's a dispute about its resolution? Like, has there?
Oh yes, definitely. So one thing that's very, very common is somebody says they proved the theorem, and quite a while later there's a mistake found. This is very, very common. So there are many different kinds of mistakes in published mathematics, by the way. There are sort of minor mistakes. So the calculational errors, or they didn't cover some exceptional case or something of this sort. And when it comes to minor mistakes that don't affect the moral of the story in some sense, I would even say probably most mathematics papers contain mistakes like that. When it comes to serious mistakes, they're more rare, but I wouldn't be surprised if a substantial percentage of mathematics papers contain serious mistakes as well. And this kind of thing is discovered often much later as well, when the result becomes of enough importance to somebody else that they start looking at it very carefully. And I hope it's okay if I say physics papers probably also contain a lot of mistakes, right? This is a normal process, this process of correcting at a later date. That's very common. Also, not uncommon, well, much less common, but also interesting is there are instances where something was thought to be in error, and years later, or even decades later, people figure out that it's basically correct. That also has happened. Most importantly, there was the work of a German engineer named Kurt Hegner about problems that are not so far from this algebraic number theory problems. And he wrote this paper in the 1960s, and people thought it was wrong at that time. And about 30 years later, other people found out that it wasn't written perfectly. There were many minor errors, in other words, but his argument was basically correct. That happened as well. So it's a very, very dynamic process because this is a human process. Yeah? It's not something that's run by the kind of machines that Russell and Haidt had hoped for. There was some other question?
Yeah. This is a wonderful presentation on ABC conjecture.
Mm-hmm.
So the motivation for this conjecture that you developed, was it the same that led the two mathematicians to conjecture it?
That's very interesting. No, but the short answer is no, I think. I don't know the history very well. So again, forgive me, whoever is listening online, if I get this wrong. But I think at the time that the two mathematicians, Masser and Oesterle, made this conjecture, I think they were motivated by Fermat's last theorem. This was a big motivation for them because the ABC conjecture would prove Fermat's last theorem for large exponents. But by the time Mochizuki was writing his paper, that had been done already. Fermat's last theorem had been proven in a different way. But again, I do want to emphasize the fact that the conjecture still gives a structural explanation of the theorem, not just a proof. And so that is still very important. So in some way, there's still significant applications to Fermat's last theorem, even though it doesn't need to be proved again. Does that make sense? Sorry, there was a question up here.
Sir, is there a way to generalize the equation?
You'll get the next question, yeah, sorry.
Is there a way to like generalize the equation for more than 3 numbers?
Oh yes, there have been a lot of generalizations worked out. That's right. That is generalization of the conjecture. Yeah. But nothing proved. Yeah. Thank you. So actually, that's a very good question, and I don't know. Are you a mathematics student? You're just interested in mathematics. So one way of sort of nurturing one's interest in mathematics is when one hears a theorem or a conjecture like this, and suppose you ask a question. Suppose I look at the equation A plus B plus C equals D instead of A plus B equals C, right? So what can I say about it? Then it's actually an interesting challenge to even formulate a plausible statement about this situation, right? And trying to formulate something like that for yourself is an excellent exercise. Yeah.
So how did the name the ABC mysteries come? Because like I've actually read it. I'm a good avid reader of detective stories, and there is a book by Agatha Christie called the ABC mysteries. So is there any relationship?
I think essentially, I'm sorry, what's your name? Shloka. Shloka, yeah. Shloka is simply pointing to me, blaming me for false advertisement. I think that's what she's saying, right? The ABC conjecture was named the ABC conjecture because people just named the numbers in question A plus B equals C, right? That's why the ABC conjecture came about. But then all this confusion surrounding it developed. Right? And people, at least a lot of people would think that we still don't know whether the conjecture is true or not, whether the proof is true or not, right? So I thought it might be reasonable to describe it as a mystery, right? But also I knew that there are people who like Agatha Christie and who might be intrigued by the title like you and come to listen to the story anyways. And so I'm so afraid you were trapped by the title. I hope you're not too disappointed. Are you disappointed? Okay, thank you. Yeah.
So, sir, at the start of the talk, you mentioned about a lot of mathematicians like discussing about the ABC conjectures proof and like having sessions where they discuss about it.
Right,
but you never mentioned about the author himself, Mochizuki, giving a talk or explaining his own theorem. So
that's a very good question. When we had that workshop in Oxford, so I was there, I was an organizer of that workshop, so of course I was there. But he participated online.
Oh.
But in fact, when we got to that thorny part of the paper, right, it was very difficult to communicate at that point. He gave very clear explanation for a lot of the paper, but at that point, I personally found it somewhat difficult to follow. But on that occasion, he participated online. But one of the very interesting thing about Shinichi Mochizuki, he's an extremely concentrated mathematician. He's working all the time. So he almost never travels. That's among the difficulties that give rise to this problem of communication.
But like, did he ever give talks where he is trying to, explain his proofs?
So my impression is he gave a number of talks in Kyoto and Tokyo around Japan, but almost never came outside. I may be mistaken about it, but I essentially never travels far anyways. Maybe from Kyoto to Tokyo, but not otherwise. That's my impression. So this has contributed to the lack of communication and understanding. Maybe, and actually, so since you asked that question, maybe that's a good excuse for me to mention one other motivation for my giving this talk. See, in my view, all the people involved, the protagonists I mentioned today, Mochizuki, Shotze, Kirti Joshi, these are brilliant mathematicians, all of them. And I know all of them fairly well. And they're very good people too. So, but somehow, this impasse is arising because of lack of communication. And I do think, eventually, if they approach the communication problem with greater compassion, that might lead to some breakthrough.
Thank you.
Hi, sir. Thank you for the amazing talk. Could you please comment on the art of thinking mathematically? How do you think like a mathematician?
Oh, wow, yeah, the big question. How does I think as a mathematician? One cowardly answer to your question, right, is that all mathematicians think differently. So it's hard to know how one thinks as a mathematician, right? So for example, we could ask the question, do mathematicians and physicists think very differently, right? It's not so clear, right? I think the ways of thinking between a mathematician and a physicist are much more similar than different, essentially. So how does one think as a mathematician? And so firstly, I don't know an answer to that question, but I do believe somewhat in my cowardly answer. They all think differently, so it's hard to say in general. But if your question, for example, so when I'm giving talks in Korea, where people tends to be obsessed about mathematics education. I don't know if they are here, but in Korea, people are completely obsessed with how to do mathematics education, how can I get children to be better at math, and so on. Right? And about that, I have an answer which I believe in more strongly. Anybody with sufficient interest who pays attention for a long time can do mathematical thinking at a high level. That I do believe. Does that sort of answer your question? Yes, thank you.
Questions? You have a question?
You mentioned Fermat's last theorem as being explained by this, but you can imagine many other. So if this conjecture were proved or will be proven later, you would imagine many other variants of Fermat's theorem also being proved.
Sure.
That's an obvious way in which this would lead to many other new results. Are there any other dramatically open conjectures or results that would follow from the proof of this?
Yes. So one thing that I didn't mention is so there was something called the effective model conjecture. So this has to do with equations of two variables, fxy equals 0, right? Where this is a polynomial equation with integer coefficient, something like that, right? And there's a problem, the following problem. The problem is to list all possible rational solutions to this equation. This is a very, very difficult problem. Yeah. So to find some solutions, often it's easy, like Fermat's equation. You may know some solutions, some easy solutions, but it's very hard to know typically if you have all of the solutions. So the problem, effective model problem, is the problem of listing all solutions to two variable equations like this. And ABC conjecture implies that there is an algorithm for solving this. That's one of the major consequences, which somehow makes a practical and conceptual breakthrough within the history of the study of equations.
I have one more question.
Is there any study that has been conducted to determine the upper or the lower bound for the weighted average multiplicity of rational numbers or complex numbers?
Well, this question only makes sense for natural numbers, right? Because the multiplicity has to do with prime factorization. Right? So complex numbers don't have prime factorization. Now, but I mentioned already that for the weighted average multiplicity of ABC triples, people have computed a lot. And found that within their computation, the largest they found was 4.9, things like that. So there's a lot of computer experiments. That's one thing for natural ABC triples. Does that sort of answer your question? Yeah, thank you. So yeah, the rational ABC, that's right. Oh yeah, thank you for pointing that out. If you have A plus B equals 3, where A, B, C are rational, then you can write that as an integer equation and sort of put it into this ABC conjecture framework. Yeah, thank you for pointing that out as well.
Thank you.
We have one question from the online participants.
Uh-huh.
Shomodev Chowdhury is asking, do we have enough computational resources to check whether the WAM value barely crosses 3.1 for gigantic primes?
Sorry, I didn't quite understand the question.
Do we have enough computational resources to check whether the WAM value barely crosses 3.1 for gigantic primes, huge primes?
Do we have enough computational resources to
check this criterion? The weighted average.
I mean, well, I'm not sure I understand the question because, in fact, the statement is saying that it's bounded by 3.1 for all but finitely many. That's not something you can prove by computation. It has to be proved theoretically somehow. You can find computational evidence for it, and people have done that, right? But it's not something that you can prove using computation. However, there is a way, that does bring up another favorite theme of mine. A lot of mathematical conjectures also can be thought of as similar to physical theories in physics. Yeah? So in physics, you have theories like Newton's laws of motion or action principles for theory of elementary particles. These are not things you prove, right? But there are various consequences you'll go out and observe in nature, right? And then the more consequences come out to be compatible with that theory, the more and more you believe it, right? So the computations so far where you assume the conjecture, if you regarded the conjecture as a theory, seem to lend a lot of credence to the conjecture. So that's a kind of aspect of it, that you can't prove the conjecture, similar to how you don't prove theories by looking at experimental consequences, but you get more and more evidence for it. And that people have done. Okay, there's one question over there.
One last question.
Sir, if it's a question which says like, if this conjecture is proved in future,
right?
Which field of physics do you feel it might be helpful for?
Field of physics?
Yes, according to you.
No. Well, unless some of my wild fantasies are true, I doubt there will be applications to physics. That's the short answer. I don't think that it really is. There's no obvious way in which it's relevant to physics. It would be great if there were.
If there are no further questions, let's thank the speaker.
Well, thank you very much for all your questions.